Thank you, Connor. So the task we are focusing on in our research is measuring poverty and health data on low and middle income countries. And the task is challenging in itself, but the best way to do it are traditional surveys that have the drawbacks of being costly, but also, and hence they are costly, they are not done on all places, hence they can be infrequent. So what researchers have been doing and very successfully doing is using satellite images to predict those scores. But satellite images do not capture, for example, historical or cultural contexts. Hence, we thought what could be done is fusing satellite images with textual data that could be sourced from the internet. And two ways of doing that is using an AI agent to perform a web search, or using LLM-generated text, where the assumption is that LLMs, as they have been trained on internet data, have the poverty information imprinted on their weights. So we fuse satellite images with these textual data as described and want to explore whether there is a convergence. So, for example, a Platonic representation that that can be shown across these modalities, or the agent induces novel information for poverty mapping. So we obviously fuse the models and very shockingly outperform vision-only scores, which are kind of the state of the art for poverty prediction at the moment. And we outperformed very significantly with our fused model, fusing all modalities, showing that there is information in those texts that hasn't been imprinted in the satellite images. And we also show that there is partial convergence in the embeddings between images and text data. So the embeddings show a cosine similarity of roughly 0.6. And as our last contribution, we also release all of the data we generated and crawled as a data set for over 60,000 DHS clusters. So basically our problem that we define is that images which are M in this diagram do not have all the information imprinted. Of course, not all the information imprinted that can be relevant for poverty prediction or wealth prediction. And hence we can add additional context by using textual data. Of course, there are other texts than internet as well, but internet is probably the most easy way to access textual data in a very sufficiently in sufficient amounts. And the two ways we are then investigating is using the LLM-generated texts, as I described, assuming that they have knowledge imprinted in their weights, or an AI agent that can crawl, for example, Wikipedia or news websites and then generate a summary based on those search results, or use the search results as they come and completely use all the search phrases.
Yeah, so just to add a little bit of context here, the ultimate task is predicting this YI, this poverty variable, and there are all sorts of background factors that influence poverty. Those background factors that influence poverty are also affecting other things like the imagery of a particular neighborhood. So a rich neighborhood or a poor neighborhood will look very different from the sky based on roof quality, based on home size, based on all these different things. So the relationship between this YI and MI is based on all those kind of built environment factors that are embedded in imagery that have been well studied in the literature. The difference here is this W. So we have the M, which is the text, the B, which is the background factors, and then this W, which are all the other texts that contain information about these background factors that are relevant to poverty. Things, descriptions about a place on the internet, all the reviews about the restaurants in a neighborhood, all this large scale, planetary scale data source, text data source, is going to be relevant to these places and gets imprinted on the weights of the neural network during training. It also gets imprinted on the weights of the AI search agent that we're going to talk about in a minute. But the search agent has an additional ability that the LLM doesn't have. The LLM has information about each place imprinted on its weights, but the AI agent, as we'll discuss in a minute, can actually query the internet to learn more about blind spots, to learn more about things that the LLM doesn't understand, to get a better, more holistic understanding of the place. So a moment ago, when Satya was talking about this agent-induced novelty hypothesis, the key question was, is the ability of the agent to gather additional texts to address blind spots that it has, is that injecting an additional layer or level of novelty compared to just looking at imagery alone, or compared to just looking at the imprinting of these texts, of these place-specific texts on the weights of the neural network? And then these W's on the bottom, those are just a few different ways that we're going to try to kind of squeeze juice out of the weights of the LLM. We're going to ask the LLM to describe the place. We're going to ask the AI search agent to give a summary of everything it read. And then we're also going to examine the traces, the full context that the search agent saw when it was scouring the internet looking for relevant information about this place. So that's a bit more context, and we'll move on now to the next slide here, which is going to cover the hypotheses in a little bit more detail.
Yeah, great. Thanks for the context, Connor. So our two hypotheses that I described briefly at the beginning are, of course, either the Platonic Representation Hypothesis, which has been proposed in the literature, where the assumption is that all the modalities converge to each other, meaning that they have a shared representation, kind of just encoded into different modalities, maybe. And the alternative hypothesis we are investigating is whether the agent induces novel information. So our search agent, which can reason on itself and think, whether the agent then adds unique structures, which then induce a novelty to help and aid the prediction of the scores.
So one of the co-authors on this paper used the analogy of the five senses when discussing the Platonic representation hypothesis. So that co-author is Adel, who's unable to join us today. But Adel was using the analogy to the senses. So we humans have five senses, and we have sight, we have touch, we have smell, we have these different senses, and these senses characterize different aspects of our environment. The Platonic representation hypothesis says that in some deep way, all of these senses correspond to the same thing, and with enough data, these senses will in some way overlap, where the information generated from them can be aligned with a better and better approximation. So that's the Platonic representation hypothesis. And as Satya was saying, the agent, if the Platonic representation hypothesis doesn't hold, at least in the limit, that would suggest that we really need five unique senses. So we're asking, is agentic ability almost like a sixth sense, a sense that can't be reduced to the others, or is it reducible? So that's what we have there. Now let's just recapping what we've already talked about. So the dotted arrow is allowing us to test this agent-induced novelty hypothesis. So now we'll go to some of the prompts that we used in performing the experiments that we'll discuss in a minute. So I'll throw the ball back to Satya for walking us through these prompts.
Yeah, so we tried to use as similar prompts as possible for both of the approaches, just to aid comparability of like the LLM-only pipeline and the AI agent pipeline. So the given information is the same. So we input a geocoded address together with latitude, like coordinates, latitude, longitude, and the year. Why we use geocoded address is because it has been shown in literature that LLMs in general can process addresses much better than just using coordinates, which totally makes sense. So both of the LLMs, or the LLM and the AI agent, are both told to then either search the web for enough content on these given informations, or just use their own knowledge that they have been building up during their training phase, and then give a description in the case of of the LLM doing the neural memory reconstruction, as we call, like the using the own knowledge, and then we just get out of the LLM pipeline a justification why it thinks this location has this in the score, and this is the description that we then use for the location. And we also get a predicted value for both of the pipelines, and a confidence, which we have been investigating, but there hasn't been much information that could be gained from the confidence values. And so if we go to the AI search agent, the only thing differing, you can see like it's very, very similar in these distilled prompts that we show here. But we search the web instead of just using the own knowledge. And we then still try to generate one justification, which then is the summary that we mentioned. So the summary that the AI agent builds based on the AI, on the search results it has been gathering. And then it also predicts a value for the location, and also the confidence score. For the other way, where we use the traces purely, we just ignore this output, so the justification and the predicted values and the confidence, and just use the search traces the agent has been choosing for this task.
So a trace, for those who aren't familiar with the term, it's basically the whole set of information that the AI search agent was able to see, was able to examine during the course of the agent's investigation. So that's what a trace is here. Question for you, Satya. Going into the project, which of these two approaches did you think was going to give better results? Which of these two approaches did you think was going to yield more accurate predictions for continent scale wealth measures?
Yeah, I mean, I think we were all thinking that the AI agent would actually perform way better, because it's just like, if you think of it, the AI agent is the LLM NMR boosted with search. So my intuition was that the boost, or the additional data and the additional ability to search like the web and use tools should give it an edge over the LLM NMR, which just uses its own knowledge. Yeah, I mean,
Yeah, the same. I thought the
proven
same.
wrong. Yeah.
We're using here the same LLM backbone, and the only difference is one is empowered with agentic abilities and the other one isn't. So you think, more is more, but we might find something a bit different. So stay with us as we get through soon to the results. This here is a visualization of the agentic workflow. For that workflow, we used LangGraph, which is a great open source tool that I'd highly recommend. And we should have links to our code as well as data in the description. So this is the workflow where we have an LLM acting as the brain or the orchestrator for this task. So the input, that was the prompt we just had. The prompt is basically we give the agent a place, and we give the agent access to different tools, web search and Wikipedia search. We give it the year, and we basically say, search the internet, search Wikipedia for as much information as you can find relevant to the International Wealth Index. We're going to talk later on about information leakage too, but this was the task, and this is just a visualization for the LLM, which can call different tools. In this case, the two tools are web search and Wikipedia search, which are operationalized as two distinct tools here. And the LLM can act by performing searches on those different tools, getting results, getting observations, and then performing additional actions on the same or different tools. We set the total number of recursive tool call episodes to 20 in these investigations, although we found that in practice, the agent was concluding its search after at most, I think it was 3 different iteration cycles of searching, getting results, and then searching again. So we're actively thinking about in future research how we can use not only one agent but also multiple agents in more sophisticated chains of agentic tool calling. But you'll have to wait to our next paper to learn more about that. So this is a bit of our agentic workflow. And now we'll talk about the 3 resulting data sets that are on Hugging Face. So I'll throw the ball back to you, Satya, to talk a bit about this.
Yeah, great. So the data we used is based on the DHS surveys that we have, because that is kind of our ground truth data. And we'll come to the problems with that later as well. But so our data set is built around over 60,000 DHS clusters where we have the survey data on the poverty score that they gave for each neighborhood. And this is all across Africa. And from the 90s up until the 2020s.
So
And
just to two finger on that. So that involved people going to neighborhoods and asking hundreds of questions of citizens across dozens and dozens of countries across the continent of Africa. So you can imagine the cost and the scale involved here to get information about household wealth in these contexts. This is a massive amount of work, a massive amount of capital, literally hundreds, tens, if not over the long term, hundreds of millions of dollars being spent to get the ground truth data here from these DHS surveys. And then that leads us to the satellite images as well, which, Satya, can you talk about how the satellite images are needed to explore Platonic convergence?
yeah, I mean, we need those because that is our second modality, right? We have the textual modality, and we also test the convergence based on just like between those 2 textual modalities as well. But the most interesting one is probably the comparison of visual data against the textual data. And there is also like a huge difference in how the kind of, if you say that each is just a representation of poverty information, like each modality, then the representation between satellite images and LLM generated text, for example, is very, very different. And what we then try to test is whether these representations are actually showing the same, or whether they maybe have their own filter, kind of like, and context that each modality cannot see, where the other one provides more insight. Yeah.
Great. So on this Hugging Face, we make available the images as well as the various descriptions used in the LLM-only neural memory reconstruction pipeline, along with the traces and the summaries from the agentic pipeline. So they're on Hugging Face. The link again will be in the description.
Yeah. So let's dive into the implementation, kind of, right? So we have those different pipelines. We have the visual only pipeline, which has been produced in the literature by many researchers very successfully. So that is kind of our baseline. That was the one that we were trying to beat, and we successfully beat as well. The second pipeline is using LLM knowledge only. So that's our LLM neural memory reconstruction, where we are back to the visual model. So we take the satellite images and take a pre-trained model that has been proven, a vision transformer, and encode those images and generate embeddings, which we then process to predict our scores. And the LLM generated texts are then also encoded, and so those embeddings are also the ones that we will compare against. So embeddings produced either by a vision transformer or transformer-based encoder models for the textual data. And so we have the two text-only pipelines. One is the LLM-NMR, and one is the AI search agent, where we used the complete traces because that was the best performing version of the AI agent instead of using, for example, the summary that the AI agent produced based on its search traces. And then we also investigated the joint performance of each. So LLM-NMR with vision, AI search agent with vision, and also the fully combined version where we use all the three modalities and predict an IWI score altogether.
Great.
And to also like to investigate our approach and like to evaluate it properly, we decided on three splits. We took like the random split, but also an out-of-country split where countries where our models were trained on weren't in the test split, and vice versa. And the out of time was year-wise, so we never had years in the test split that were also in the train split. And of course, we did all these through 100 iteration bootstrapping. And for the more intensive trainings, we did cross validations. The metrics we were checking on were R square and RMSE, just because they are, especially R square, very accepted in the literature for powered prediction. So to also compare the embeddings that I was talking about, we used two different embedding models for the textual data because for the visual data, there was no big need to use different models as that was an accepted uh, vision transformer for satellite images. But for the textual data, we used a frozen OpenAI embedding model, which is rather big, and then also a fine-tuned open source embedding model, which was very small. Just to compare whether there are huge differences for different embedding models or the textual data performs relatively similar across different embeddings. Yeah.
So for those who aren't familiar, frozen means we don't modify the weights of the neural network. Here, the OpenAI embedding model is, at least at the moment, as of mid 2025, a closed source model. So we don't have direct access to the weights on, for example, Hugging Face. However, for MPNet, it is an open source model, so we are able to go in and modify the weights in whatever way we would like. So that's one reason why we are using the OpenAI embeddings is frozen, meaning we don't modify them at all. Whereas for MPNet, we do modify the weights, and we modify the weights on the training set so as to generate the embedding structure that generates the most predictive poverty prediction or the most predictive output from that approach. So that's how we're fine tuning. We're fine tuning on the DHS label within a training set. Any other
Yeah.
details about evaluation here, Satya?
No, I guess if you have questions, feel free to ask, then we can encourage our discussion. But otherwise, I guess, yeah, that's it.
All right. Let's get to performance. What do we find?
Yeah, this is the most interesting part. So the very shocking result for us is that we could beat vision only by such huge margins, and that the LLM only, like without combining with anything, did beat the vision only baseline that we used. And if combined with visual, it was even better. So it's very interesting to see that even though that for each combination there or for each modality that is added as a into the fusion, the models perform better and better. Um, so you can see that the AI search agent, very surprisingly, could not match the performance of the LLM NMR. So the AI search agent was best performing on the search traces, so on complete traces. And that hence we only use that version of the AI search agent for our fusion experiments. The same for the LLM-NMR, where we only used our best performing approach, which was using Llama for Maverick, and we then inspected the performance of that fused with the vision only and with the traces. So yeah, I think many surprises here. A search agent not performing as good as the LLM-NMR and LLM-NMR performing even better than vision only is, I think, very, very interesting. And the embedding models show like very consistent results. So the MPNet, as it is way smaller than the OpenAI embedding model, performs not as good, but it still shows the same. Yeah, it shows similar comparative performance.
Yeah, so those were some of the surprises. And another thing that wasn't surprising, I guess, there were a ton of surprises. The one thing that wasn't surprising, in addition to the bigger OpenAI embedding model doing better, would be that the kind of the neural reconstructions from bigger models generally perform better than the neural reconstructions from smaller models. So the Llama 4 Maverick model was the biggest one examined here, and it gave the best neural reconstructions compared to the other approaches that use smaller LLMs. So that would be another finding from this. But the big picture would be there is a boost. So we do find that there is additional signal that we gain when we do use these different modalities and combine them together. And then the other big picture result here is that the agent actually seems to get confused by the long context. So there is recent work coming out about how very long reasoning traces can impair model performance. And I think that may be what's happening here, where the neural network that we're using does know a lot about the places that it's being asked to give information about, but it's also getting a bunch of other information from the search traces, some of which is relevant, but some of which isn't relevant. And that additional context seems to be, in a sense, overwhelming the neural reconstruction abilities and actually reducing performance on a relative basis, although overall there is a gain over the image-only baseline.
Yeah, exactly. So we also investigated how our models performed for different regions, kind of. So we compared the residual values, the mean residuals for each neighborhood, with the vision only, and then the best performing combined model. So just to see like CV being our so computer vision being our baseline, and we comparing, okay, where does textual data seem to add the most of information and hence performance gains. And I think what can be seen is that very, very conflict areas and also dense areas seem to be where textual data helps the most because, yeah, maybe maybe the textual data could be more fine granular than the satellite images in that case. But we can also see that in many other areas, they are actually performing very, very similar. So there is no difference, no huge difference between the vision only and the combined performance. And yeah, like if we look, for example, in the Sahara region, we can assume that satellite images struggle a lot because the images are very uniform. Hence, the textual data adds some more context. So for both extremes, if it's too homogeneous or too heterogeneous, then the textual data seems to add an edge. And also if there is like dynamic places such as conflict areas and similar. Yeah.
Yeah, for
What are
those
your
trying to make
thoughts on it?
for,
Yeah.
for those trying to make sense of this plot, red means the combined approach wins. Blue means the CV only approach wins. So overall, we see there's more red than there is blue. But as Satya is saying, there are some places where there's not much difference. We see more of a gray color, meaning the two are the same. But those regions that are more red, meaning the combined agent text approach with the imagery is doing better. That's in Somalia, Yemen, and Central Africa region, both of which areas are affected by conflict, as well as this South Africa core down here in the south. So definitely some really interesting spatial insights here. But now we're going to talk about the temporal insights. So what did we learn about the temporal dynamics here, Satya?
Yeah, I think the temporal dynamics are very interesting because we can probably also gain some insight for the leakage issues that we will talk about later. But what we can see here is again the residual difference of the CV only, so the vision only model, and compared to the combined version, the best performing model. And so if the score is high, then the combined model won, and if it's low, then it's very similar. And we can see that it consistently outperforms the vision-only model. So there is no year that the vision-only model actually outperformed the combined approach. But kind of surprisingly, especially the 90s performed very well. So, I mean, on the one hand, there is the issue that in the 90s, the satellite images are the most scarce. So maybe that is one reason why the textual data could make such a difference in that time periods. But on the other hand, it's very interesting because one could argue that the information density that the LLMs were trained on actually was way higher in the 2000s, 2010s, up to the 20s, because yeah, the internet was booming in those years, right? And in the 90s, it was up and coming, but not yet as big as it was in the 2000s and 2010s.
Yeah, it is interesting. So we might find a big gains because we're doing a lot better, or we might find big gains because the computer vision only approach is doing a lot worse. The hypothesis here is that the gains from the 90s are from the computer vision approach doing a lot worse due to those image scarcity issues, due to Landsat privatization, among other things happening in the 1990s. So we have just a data scarcity issue there. So interesting stuff, Satya. But let's move on now to the Platonic Representation Hypothesis. The title of the paper, after all, talks about that. So what did we find about convergence of modalities?
Yeah, I mean, one of our most surprising findings was, of course, that the LLM-NMR was beating the AI agent by quite a margin. So that supports the Platonic hypothesis more than the AI agent-induced novelty, because the AI agent assumingly couldn't introduce so much novel information that was aiding the prediction performance. Um, and also, like as I mentioned in the beginning, the convergence of the different modalities was quite high. So it had a cosine similarity of 0.6 for the if we compare those embeddings, which are in the same dimension, and we also aligned them with canonical correlation analysis just uh, to show more realistic results, not just using the embeddings as they come out of the different embedding models, but aligning them um, through CCA. And the search agent was also similar to LLM. So I guess, yeah, Connor, what do you say? Do is the AI agent did the AI agent induce some novelty? What are your thoughts on that?
So we saw that the best performing approach did combine the computer vision plus the neural memory reconstruction plus the agent traces. So from that sense or perspective, there may be a degree of novel information contained within the agent traces, although there are marginal gains. And also these cosine similarities within aligned representation space across modalities is pretty high, 0.6 cosine similarity. So my sense is overall there's strong evidence for Platonic representations here, and weak at best evidence for agent-induced novelty. The one thing I will say is that the 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 agent traces are long. Those contexts are pretty long. So more sophisticated summarization strategies might extract better information from those agent traces in order to potentially, in a sense, emphasize or highlight the unique or novel portion of the agent traces. So I think there's definitely a lot of work to be done on reinforcement learning approaches towards agentic data extraction that we can pursue in future work. But broadly speaking, I would say we have support for Platonic over novelty. But future work will really, I think, answer that question in a more conclusive way when we bring more sophisticated data extraction and information retrieval mechanisms within the agent pipeline.
Yeah, so getting back to the alignment of our two modalities, we showed like the cosine similarity, and just to also um, show you a visualization, we have that matrix on the right side, which just plots the cosine similarity for each embedding pair in the textual space and the image space. And we can see that there is a lighter line. So the yellow meaning the cosine similarity is higher, and the dark blue meaning that the cosine similarity is rather low.
And
And
how are these data arranged? Can you talk a little bit about that?
yeah. So we sorted them by latitude, right? Yeah.
Yes.
We sorted them by latitude. So just we could maybe also gain some insights on the pairs that like the performance over Africa, the vertically over Africa. So um, we see that the cosine similarities are very high in yeah, kind of the middle, but also in direction of the bottom of Africa. Um, yeah, that's the insight we can gain from the arrangement.
You can also think about this almost as an adjacency matrix where the color is lighter. There's more similarity between image and text, embeddings from one place to another place. So along the diagonal, that's basically looking at the image modality compared against the text modality for a particular place. So that diagonal is what we're plotting the histogram of in the left plot. The right plot is looking at this text image alignment, not only, place A text versus place A image, but place A image against place B text and place A image against place C text. And that whole collection of similarities is what we're plotting here. So where you see a lighter color, more of this yellow, that's where there's more of this alignment across modalities. And one of the interesting things here is there are these blocks of similarities. We also find that latitude doesn't tell the whole story when it comes to similarity. So we see that there are some off diagonal blocks here that are pretty well activated, which seems to suggest that across the African continent, certain places, even though they might not be geographically similar, have similarities in this text image alignment um, that could indicate some deeper perspective about how development is unfolding across the continent.
Yeah, so I mean, we already dived into the limitations, kind of, right, during our talk. We have the issues with the DHS clusters being our main ground truth, and that's how our whole data structure was built, and around those clusters that was built. So these surveys are, of course, taken or tried to be taken in a way that we capture the continent, but they cannot capture all of it. So there might be some bias by using only the clusters and neighborhoods that the DHS used, and we may kind of oversee other underrepresented neighborhoods through only using those data points.
So that would be really rural places. Really rural places aren't contained within the sampling frame of the DHS. So we're not capturing those within our approach here.
Yeah, exactly. And also our whole pipeline is has potential to be extended by a lot. So we of course can scale the agent a lot. And also we can dive into the text processing more so that we maybe have a text processing method that performs equally good on the shorter descriptions generated, for example, by LLM-NMR, as it does on long texts, for example, concatenating all the search phrases that the AI agent yielded. Because uh, that inequality is existent in our embedding models because they are, as Connor mentioned, said to be sensitive to very, very long contexts and yeah, are said to be underperforming in those long context data samples. So what do we want to do? Or what can be taken out of our research, right? I think we showed that multimodal fusion improves poverty monitoring a lot. I think that's the most surprising, but also most important thing we learned out of our research. Then we could also answer the question or the hypothesis that we posed at the beginning and show some partial convergence that would support the Platonic hypothesis. The most surprising learning is that our LLM-NMR outperformed the AI agent. Although we all already mentioned the issues that could be underlying, but for now and with this pipeline and yeah, kind of this rather cost-efficient method to process the texts, we show that the LLM-NMR outperforms the agent and yields really, really good results on the prediction data, like on the poverty prediction task. So this can be taken into account for future investigations and yeah, as we say, the agent could be improved, but the LLM-NMR obviously could also be improved. And finally, we also provide our data set so that you guys can take a look into it, come up with new ideas and use it for your own research, which will yield exciting results, I'm sure.
Right. Thank you, Satya. Thank you all for listening. If you have any questions, send a comment into the comments. Reach out via email here. Take a look at the paper. Here's the paper link. It's on archive. And we also have some more information about this paper as well as others at aidevlab.org. So definitely looking forward to hearing from you. And thank you again. And we'll stop it there.